Welcome back to the deep dive. Today, we are stripping away the steel decks and looking at a system that usually just sits in the background. It hums away unnoticed until it stops.
And then it instantly becomes the single most important piece of machinery on the entire ship.
Oh, completely. And I'm your host, ready to jump in, and sitting across from me is our resident marine systems expert. We weren't talking about the main engine today, are we?
No, we are not. We're talking about the one thing preventing a complete crew mutiny when you're crossing the equator, the marine accommodation air conditioning system.
Which, looking at the research for this deep dive, I think we really need to reframe how we view this equipment. It's so easy to dismiss AC as a luxury. Just comfort cooling.
Yeah, people think of it like climate control in a car.
Exactly. But when you look at the physiological data in these reports, it's not a luxury at all. It's life support.
That is not an exaggeration, believe me. You have to consider that these vessels are operating in tropical zones. You're talking 35, maybe 40 degrees Celsius outside with 90% humidity.
Which is brutal.
It is. You lose the AC, and the accommodation block basically turns into a greenhouse. The crew can't sleep, heat stress sets in, and reaction times just drop. It becomes a genuine safety hazard for everyone on board.
So the mission here isn't just, making cold air. It's really about acting like a giant refrigerator for the ship's cabins. You are taking heat from the living quarters and throwing it out into the ocean.
Precisely. We are managing the entire environment, maintaining a comfortable temperature, usually around 22 to 25 degrees Celsius, but crucially, it's about controlling the humidity, keeping it between 50 and 60%.
Because if you just cool the air but leave it at 90% humidity...
You're going to feel like you're swimming in warm soup.
Yeah.
The marine environment is relentless with moisture.
All right, so today we're going to give you a step-by-step walkthrough of what's called the closed-loop refrigeration cycle. We'll follow the refrigerant as it travels through the four main components: the evaporator, compressor, condenser, and the expansion valve.
And we really want to get into the mechanics here, not just what the parts are, but how they actually interact.
Yeah, so let's set the stage. Imagine we are a molecule of refrigerant, and we're about to enter the space that needs cooling. Step 1, the evaporator.
Or as I like to call it, the heat sponge.
The heat sponge, I like that. So physically, this is just a big box with a fan and a coil, right? Usually tucked away somewhere. But thermodynamically, this is where the magic happens. Warm, humid air from your cabins blows over this coil.
Right. And inside that coil is low pressure, very cold refrigerant. As it absorbs the heat from that cabin air, it actually starts boiling.
Boiling, but it's cold.
Yes, because pressure and temperature are linked. At that very low pressure, the refrigerant boils at a very low temperature. So as it boils, it turns into a gas, soaking up massive amounts of heat.
Okay, so the air gets cool and goes back to the cabin. But what about the humidity? You mentioned that was a huge factor.
That is the soda can effect. If you take a cold drink outside on a hot day, water beads up on the can. The same thing happens here. The moisture in that warm cabin air condenses right onto the cold evaporator coil.
And then it just drips away.
Exactly. It drains away, and that is physically how the humidity is pulled out of the air.
That makes so much sense. Now, before we leave the evaporator, there's a technical detail from the sources we need to hit: the state of the refrigerant.
Yes. The refrigerant leaving the evaporator is now what we call a superheated vapor. It's a low-pressure, low-temperature gas. It has completely boiled off and even absorbed a little extra heat just to be safe.
To be safe. Which brings us perfectly to step 2, protection. We're moving toward the compressor through the suction line, and we hit the bouncers.
The security guards of the system?
Right, the suction filter dryer and the suction accumulator. Why do we need security here?
Well, the accumulator plays a vital role. It acts as a safety tank to catch any liquid refrigerant that might not have boiled off in the evaporator. Compressors can only handle gas.
Right, because you can't compress a liquid.
Exactly. If liquid hits those compressor pistons, it's called liquid slugging. It will absolutely destroy the compressor. The accumulator stops that from happening. It also stores excess refrigerant during low-load conditions.
So it's basically an insurance policy for the heart of the system, which is step 3, the compressor.
The heart is a great way to describe it. This is where the heavy lifting happens. Ships usually have 2 of these, by the way, one running and one on standby for safety. Though if the load is really heavy, they can both run.
So what is the compressor actually doing to this low-pressure gas?
It takes that low-pressure vapor and just squeezes it. It crushes it into a tiny volume. And physics dictates that when you do that, the pressure skyrockets and the temperature skyrockets.
So we get high-pressure, very high-temperature gas.
Correct. And because this is such a critical piece of machinery, there are several safety nets built in right here. High pressure cutouts, low pressure cutouts, and oil pressure protection.
Which leads us right into step 4, cleanup. Because during all that violent squeezing in the compressor, some lubricating oil actually escapes with the hot gas, right?
It does. It gets carried away in the flow. And you do not want oil coating the inside of your heat exchangers down the line. It acts as an insulator and ruins your efficiency.
So how do we fix that?
We use an oil separator. It's placed right after the compressor. It essentially separates the heavier oil droplets from the gas and then uses a float valve to automatically send that oil right back to the compressor crankcase.
That is incredibly clever. It keeps the system clean and ensures that compressor stays lubricated. Okay, step 5. We have hot, high-pressure gas. Now we need to reject that heat.
We need the condenser.
Right. And on a ship, we don't use giant fans like you would on a building. We use the ocean.
Yes, the condenser is a heat exchanger cooled by seawater. Seawater flows through a series of tubes, and our hot refrigerant gas flows around them.
And the heat just jumps ship, literally. It transfers from the hot gas into the colder seawater.
Exactly. And as it loses that heat, it undergoes a phase change. It cools down and condenses back into a liquid.
So it goes from a gas back to a liquid.
Right. And the technical term for the output here is high-pressure subcooled liquid.
Subcooled. Why is subcooling so crucial?
Because it prevents the liquid from turning back into a gas too early. If it flashes back into a gas while it's still in the pipes, your efficiency drops to 0. Subcooling ensures it stays a solid column of liquid.
Got it. And for reliability, the sources mentioned that there are always standby seawater pumps, right? So if one pump fails, the whole AC system doesn't just shut down.
Always. Redundancy is everything at sea.
Okay, moving down the line. Step 6, storage and inspection. The liquid line. We have something called a receiver tank.
Yes, the receiver tank stores extra liquid refrigerant. You need this to handle changes in the cooling load.
Like if a bunch of crew members suddenly come off shift and enter the cabins.
Exactly. The system needs to adapt, and the receiver provides that buffer of extra liquid.
And right after that, there is a very simple but critical diagnostic tool, the sight glass.
It's literally a little glass window built into the pipe.
And engineers are looking through this for what exactly?
They're checking for bubbles. If you see bubbles, it usually indicates low refrigerant or poor subcooling. You're also checking a tiny indicator inside for moisture. If moisture gets in, it can create acid and ruin the system.
All right, we are at the final stage. Step 7, the reset. We meet the gatekeeper, the thermostatic expansion valve, or TXV.
This is a fascinating piece of engineering. It separates the high-pressure side from the low-pressure side.
How does it know how much refrigerant to let through?
It senses the temperature at the outlet of the evaporator. Based on how warm or cold that pipe is, it opens or closes to control the flow.
And what happens when this high-pressure liquid actually squeezes through that tiny valve?
An immediate, massive drop in pressure. And as we know, a drop in pressure equals a drop in temperature.
So it instantly becomes a freezing cold mixture.
Yes, it becomes a very cold mixture of liquid and what we call flash gas. And that cold mixture is sprayed right back into the evaporator, ready to start the whole loop over again.
That is the closed-loop refrigeration cycle. It just goes round and round.
Yeah.
Okay, let's do a rapid-fire recap for you listening to lock in these states. I'll name the component, you give me the pressure summary. Ready?
Let's do it.
Leaving the evaporator.
Low pressure superheated vapor.
Leaving the compressor.
High pressure superheated vapor.
Leaving the condenser.
High pressure subcooled liquid.
And leaving the expansion valve.
Low pressure flash mixture.
Simple, clear, and perfectly balanced.
And you have to remember, this loop runs 24 hours a day, 7 days a week, nonstop, just to keep the crew safe and effective.
Which really brings us to the core message for any marine students or junior engineers listening to this right now. These systems might seem incredibly complex at first glance. There are a lot of moving parts.
There are, but understanding this specific cycle, mastering it, is exactly what makes you indispensable on a ship.
You aren't just turning wrenches or fixing machines. You are quite literally the guardian of the crew's well-being in the middle of the ocean. Without you, the ship stops functioning.
That's the responsibility of the role, so keep learning, stay curious, trace the pipes, read the gauges, and master the cycle.
Before we wrap up, I want to leave you with one final thought to mull over. We've talked exclusively about traditional chemical refrigerants today, but with new environmental regulations pushing the maritime industry towards zero emissions, think about how this exact same thermodynamic cycle will have to adapt to natural refrigerants like CO2 or or ammonia.
The pressures and safety protocols for those are a whole different ballgame.
Exactly. The cycle stays the same, but the engineering challenges are going to completely evolve. Something for you to explore on your own.
It's the future of the industry.
Well, that does it for our breakdown of the marine accommodation air conditioning system. Keep studying those technical manuals, and we'll catch you on the next deep dive.